Hey guys, welcome back to another episode of Captain Hook's Physics Problem Solving. Today we are going to talk about escape velocity. We're actually going to solve for an equation to figure out what the escape velocity of an object is, and then we'll figure out what it is from Earth and maybe use that to see if we can estimate how big a black hole might be. Okay, so first of all, when you throw a ball in the air, it usually falls back down. We're hoping you know that right now. If you throw it a little bit harder, it's going to take a little bit longer to throw back down. If you throw it so hard that it never falls back to Earth, that's called as an escape velocity. You've let it go at a velocity that it'll never return. Okay? So, we are going to first try to solve an equation for escape velocity in order to find the escape velocity of an object being launched from Earth. It gives us the radius of Earth of 6,360 kilometers and a mass of 6 times 10 to the 24th kilograms. Okay? So in order to do this, we have to use the idea of conservation of energy. Okay? So in conservation of energy, we know that mechanical energy is always conserved. So our initial mechanical energy has to equal our final mechanical energy. Okay? Now, in this case, we're dealing with kinetic and potential. So we need to sort of figure out what our initial kinetic and initial potential are for all of this. Okay? So initial kinetic energy, well, kinetic energy is 1/2 mass times velocity squared. So initial kinetic, which I'll just do with this little I, is 1/2 m initial velocity squared. Well, in this case, because our initial velocity is the speed we're letting it go at, that's actually our escape velocity. So I'm just going to rewrite it as 1/2 mve for escape squared. Okay? Our final kinetic energy, same idea, but 1/2 mv final squared is the final velocity once it's left Earth. We don't have to worry about getting sucked back down to Earth. And in this case, we want to know the exact velocity for our escape velocity that will allow us just to barely escape. So if we're just barely escaping, our final velocity has to be 0, so our final kinetic energy has to be 0. Okay? When it comes to potential energy. Now, potential energy normally is just mass times little g, acceleration due to gravity, times the height above the ground. Now, when you are dealing with something that gets much, much farther away from Earth, you can no longer use this equation. We have to use an equation that looks like potential energy is negative big G, which is our gravitational constant, big M, which is the mass of the planet, little m, which is the mass of the object, over r, which is the distance from the center of the planet to the object. Okay? So that's the equation we're going to have to use. So for our initial potential energy, again, we're going to use this, negative G, big M, which is mass of Earth, little m, mass of the object, over, I'm going to just put big R because that's actually the radius of Earth because we're going to be at the surface. Okay? Our final potential energy is going to be the exact same equation, negative G, big M of Earth, little m of the object, over the radius. But as you get really, really far away from Earth, this number gets really, really, really big, so it actually goes to infinity. So if you have an infinite number on the bottom of a fraction, this whole thing is going to go to 0. So if you notice, our final potential energy and kinetic energy are both 0. Okay? So again, now we got to put it all together. So in order to do that, we're just going to do kinetic energy initial plus potential energy initial equals, and we'll do our finals, kinetic energy final plus potential energy final. But if you don't remember, both of our final kinetic and potential energies are 0, so that just equals 0. Okay? So now if we come back in, we plug in what we know. Well, our kinetic energy initial is just 1/2 mass times the escape velocity squared, and that is the mass of our object. And then we subtract, because we're adding them, but it's a negative, G m of Earth times mass over the radius of Earth, and all of that is going to equal 0. Okay. And again, we're trying to solve for escape velocity. So we're going to subtract that to the other side, and I'm going to go to a new page real quick. So all I'm going to be doing is 1/2 mass times escape velocity squared equals just brought it to the other side. Mass of Earth times mass over the radius of Earth. Now, if you notice, there's a mass of the object on both, so we're going to cancel that out. I'm going to multiply by 2 to both sides and then take the square root. So we get the escape velocity is equal to the square root of 2 times g times the mass of Earth over the radius of Earth. Okay? So that gives us an equation. Now, we were given that the mass of Earth, so it's right over here, was 6 times 10 to the 24th kilograms. And the radius of Earth, I guess I put a big M, was 6,360 kilometers. Now you could put that into meters by multiplying by 1,000, but I'm just going to leave it like it is because it's simple enough. Okay. So if we want to find what that velocity needs to be, all we got to do is plug these two and that gravitational constant into our equation. So escape velocity equals the square root of 2 times 6.67 times 10 to the negative 11th meters cubed over kilograms times second squared times the mass of the Earth, 6 times 10 to the 24th kilograms, all over 6,360,000 meters. Again, we plug all that in. Oops. And so we got meters canceling with meters, or making it 2. Kilogram cancels with kilograms. So meter squared over second squared. Take the square root, that goes away. So we're left with meters per second. And that's 1.12 times 10 to the 4th in meters per second. Okay? So that's the speed, or the velocity. We'd have to throw something straight up to make it leave Earth. Okay? That's not too bad. All right. Now, our last part of the problem says within a certain distance of black hole, not even light can escape. This point is called the event horizon, where the speed of light is 3 times 10 to the 8th meter per second. Now, even though our equation that we solved for up above isn't exactly true, it can be used pretty well to guess about what the radius would be. It's close enough. So it wants to know what the radius of a black hole would be with the same mass as our sun, which it says is 2.0 times 10 to the 30th kilogram. And it says our sun, as just a comparison, has a radius of 7 times 10 to the 8th meters. So again, we're going to use the same equation that we solved for before. So I'm just going to rewrite that real quick. Our escape velocity is just the square root of 2 times the gravitational constant times the mass of, in this case, the black hole, over the radius of the black hole. So in this case, we're solving for radius. So I'm just going to square everything and do a cross multiplication. And I'm going to save you guys a little bit of time by not doing each step. So we just know that the radius is going to end up equaling 2 times g times m, which is again the mass of our black hole, over our escape velocity squared. Okay. So if we plug all this in, we do r equals, well, we have 2 times 6.67 times 10 to the negative 11th. Again, this is our gravitational constant, meters cubed over kilograms times second squared times the mass, in this case of our sun or the black hole, was 2.0 times 10 to the 30th kilograms, divided by our escape velocity squared, where in this case we're dealing with the escape velocity of light, which is what we said sort of defines our event horizon. So 3.0 times 10 to the 8th meters per second, quantity squared. So we're going to be left with, well, 2 of the meters go away, 2 of the seconds go away, kilograms cancel out, we're just going to be left with meters, which is what we want for a radius. And again, we plug all that in, and it's about 2,964 meters, which we can round off to about 3.0 kilometers. So if we compare that to what we had for the sun, which was 7 times 10 to the 8th meters, it is much, much, much smaller Same mass of our sun, very, very small space.